All right, so in this example, we're going to look at the matrix of a nilpotent matrix, or a transformation. So suppose we just work in F4 to keep things straightforward, and we'll have this transform n, which just takes each coordinate entry and moves it successively down the chain. So it's like a shift on a finite dimensional space. Okay, and so we can, if we take v to be the vector 1, 0, 0, 0, and then we take, we apply n to it, and we get nv, then every entry is going to get shifted one to the right, and then doing that again, and then finally doing it one last time, we get 0, 0, 0, 1. And then applying n anymore is going to evidently give you 0. So you can see there's definitely nilpotent here. And so now following the book, I'm going to note that this is a basis and then number it in kind of the reverse order of what you'd think. So if we take v1 to be this guy, and v2 to be this guy, and v3 to be this guy, and then v4 to be this guy. Now we'll look at the so this is a basis. In fact, it's the standard basis, just enumerated in reverse. So let's see. So now to find the matrix of the transform n, recall that we find the entries for the matrix T by looking at what happens when you apply it to the kth basis vector. And so then we express that in terms of the basis vectors. Oops, that's v1 plus all the way up through a n k v n. And so this guy here is the kth column, and so in particular the A's are the entries of the kth column. Notice that the second coordinate is fixed equal to k. So okay, so the first column, if I can spell column, is going to be, let's see, well, we apply n to v1 and see what we get. So we're applying n to just about to do it wrong here, 0, 0, 0, 1, and so that shifts that 1 off the end, and we get the 0 element. I'll just write it as 0. Okay, and so then that tells us that the first column of our matrix is all zeros, so we've got that much so far. Now, if we look at the second column, so this is going to be n applied to v2, and so that's n of 0, 0, 0, 1, 0, there we go. And so then when we shift it, we're going to end up with 0, 0, 0, 1, and that's what it looks like in terms of coordinates, in terms of the basis vectors. So that's the basis vector v1 with coefficient 1 and nothing else. So the second column that we have here is 1, 0, 0, 0. Maybe space that in a little bit. There we go. Okay. Third column is the image of v3 under coordinates, so that's v2, and so v2 has the expression 0v1 plus 1v2 plus 0v3 plus 0v4, and so it looks like 0, 1, 0, 0. And the fourth column is the coordinates for the image of v4. which is 1v3. Okay, and so putting that all together, you can see that the matrix for n has zeros coming down the diagonal, and then a 1, 1, 1, and a 0 elsewhere. Okay, so that's a simple nilpotent. Let's look now at a slightly more complicated nilpotent. And this actually gives a pretty good idea of the general case, what kind of stuff you can have going on. So we'll take n, z1, z2, z3, z4, z5 defined to be 0. And so we're going to shift the first two over. And then we're going to kill one, and we're going to shift the fourth one over as well. Okay, so now look what happens. If we start with 1, 0, 0, 0, 0, and we apply the transformation n to it, then we'll get 0, 1, 0, 0, 0. And if we apply n again, we'll get 0, 0, 1, 0, 0. And if we apply it again, then it's dead. But we only got 3 here. So in this situation, v n squared v is not a basis because we didn't get enough elements. We only got 3 things, and we're looking for a basis of f5, which is 5-dimensional. But all is not lost. We just need another sort of starting point. So if we start with this guy, then hitting it with n will get us here, and then it's dead. But now we got 2 more vectors. So if we call the first one like v1 and nv1 and n squared, oops, v1, somehow I forgot to write v1 after that guy. Then down here we also have v2 and nv2, and the first 3 did not give a basis, but all 5 together do form a basis because they're all clearly linearly independent and 5-dimensional, and we're in a 5-dimensional space. Well, that plus the fact that this is obviously the standard unit basis. So our basis looks like n squared v, n squared v1, n v1, v1, and then n v2, and then v2. And if you look at the matrix of n in this basis, it looks like this. So here I'm writing it in block diagonal form. So here's the blocks on the diagonal, and then here's the zone of all zeros where nothing can survive. Okay. All right, and so you can see there's the 3-dimensional subspace spanned by the first 3 vectors, and then the 2-dimensional subspace spanned by the second 2 basis vectors. So in the next clip, we're going to see a theorem that tells us that every nilpotent has a basis that gives it a matrix of this form.